Okay, today should go pretty quick. So we're really not doing anything new. So we're going to look at significance tests for means. So just kind of a little review on yesterday's lesson. So yesterday we did confidence intervals for means. All right, so here's some important things. Proportions are used with categorical data. And that's when you can split your data into successes, which is when we test this, n plus p, and our failures. So n times 1 minus p. So our successes and our failures. And means are used with quantitative data. And I would tell you that one big thing here between this is that with quantitative data, you have to have a unit on your answer. All right, we don't just say the proportion is, we're going to say the mean is something grams or something days. So when n is less than 30, so we don't meet our large condition, and you check for normality, you have to do this by graphing the sample. And we did this yesterday, and it's going to continue into today. So we're not trying to prove that the sample data is normal, but rather trying to infer something about the population. So what we're trying to do here is we're looking for skewness or outliers. And remember, you have to play with your scale to make sure that you're not just looking at the first scale that pops up on your histogram. And normally now, I think with the AP test, it's going to give you the graph. Okay, so we're going to use a t distribution, and we need a sampling of the t distribution of our sample statistic. We want that to be approximately normal, which is why we still check the normal condition. We talked about this. We know that this would be our normal graph, and then I would have something that looks like this with a higher tail here on the end for my t distribution. You might see it written as t star. That's how you're really probably going to always see it in this class, but it could also be t star and then the subscript n minus 1. And remember, n minus 1 just represents your degrees of freedom. Okay, now this is something that's new, and I know that we've talked about this earlier in the year, but this just says if your conditions are not met, so it's not a random sample, it's not within 10%, it has outliers, draw attention to it and then continue with your inference procedure. In your conclusion, what you're going to want to say is that it might not be reliable because the conditions were not met. So still check them. If it doesn't work, don't stop. Keep doing it, but then just draw attention to it in your conclusion. Okay, so now let's go back and review for just a second significance tests. So what should you have gotten out of our proportion significance tests? So a null hypothesis is the claim of no difference related to our population parameter. So what this means is that we always have an equal situation. And the alternative hypothesis is where we're trying to find evidence for greater than, less than, or different from the null hypothesis. So what this looks like in terms of means is that my null hypothesis is going to be the mean is going to equal our population mean. And our alternative hypothesis is going to be anything greater than, less than, or not equal to this value. Our significance level, our threshold for rejecting goes back to the significance level, and it's usually 10, 5, or 1%. And this corresponds to a 90% confidence interval, 95, or 99% confidence intervals. All right, so our test statistic, when we find the test statistic, we want to see how far away that this is from our sample statistic. Y'all, hold on, my lights just went out. Let me see if I can get it back on. All right, so what does this mean? This is not anything different. So we looked at this before as our Z statistic. So now we're looking at T, but nothing's really changed here. We still have our statistic minus the parameter over our standard error. Okay, so this hasn't changed. So if we look at just our normal Z-score, we would have X bar minus our population mean over our sigma, which was our standard deviation of the population. All right, so our p-value, again, this doesn't change. Our p-value is calculated from the test statistic, and it tells us the probability that we get this statistic, so the probability that we get X bar, or more extreme in the direction of the alternative, so less than or greater than or two-sided, so all of this is still there, when the p-value is less than sigma, we can reject the null. And when the p-value is greater, then we fail to reject the null. Okay? And then again, this hasn't changed. We do or we do not have convincing evidence. All right, so all that's review. So let's talk specifically now about what our alternative hypothesis would look like if we have this p-value that we're looking for. So if I say in my alternative that it is less than my mean, what I'm looking for here is I'm going to have some t-value, some t-star value. If it's less than, I'm looking for this part of my tail. All right? Remember, the t-star tells us we're looking for the tail. If I have something that is, let's greater than, then what that will look like is I'm going to have a positive t-star, and I want to know this value of my tail. And finally, if it is just not equal, so we don't know what that value is, I'm going to have a negative t-star and a positive t-star, and this is my two-sided interval. Okay, so we're looking at the combined area on this guy. Okay, so let's get into specifics for conducting a significance test for a mean, not a population. So when conditions are met, the test statistic is going to be a one sample t-test. And remember, this is assuming we do not know our population standard deviation. This is when we don't know this guy. Okay, so what does that look like? So my t-value is my x bar minus my population mean, or my claimed mean, over the standard deviation of my sample over n. So let me highlight a couple things. So this is my sample mean. This is my claim. This is my sample standard deviation, and this is my sample size. And this only works, we use this formula, if we do not know our population standard deviation. Okay, so T here has an n minus 1 degrees of freedom. X bar and S come from your sample data, and this is most often we're going to use a one var test to get all of our data. Because it's coming from sample data, this is why we use this standard error. And if you know sigma, which is what I just set up here, then we would perform a one sample z-test. All right, so the big thing here, and this is my formula for this, my z for this guy. Now, here's the thing. We're going to have to identify our standard deviation as either a sample standard deviation or a population standard deviation. It will tell you if it's a population standard deviation. Okay, so next thing that I have here. Once we have our t statistic, we're going to use t-CDF. So we don't use normal CDF anymore. We're going to use this. So not normal CDF. And that's going to give us our p-value. And then we're going to still check conditions the same way. So I know you've seen this a million times. So random assignment. Independence, we're checking our 10% condition. What we were hoping for here is that n is greater than 30. And then the central limit theorem tells it this approximately normal. If n is less than 30, we have to either have the original population be approximately normally distributed, it'll tell you that in your problem, or we have to graph the sample data. All right, so let's get right into an example problem. So, your AP Stats teacher believes the average number of minutes their students spend on homework every night is greater than 30 minutes. She randomly selects a sample of 10 students and records the number of minutes they spent on homework last night. Here's the data. Is there convincing evidence that at the 10% significance level of your teacher's beliefs? So my communicate part here. So my mu is going to be my average. So this is my mean or my average. I'm just going to say average because they use average. So the average number of minutes a student spends on homework. So what is, and this is a test, and we know this because it tells us right here significance level. So my null hypothesis here is that the average student spends 35 minutes. And it tells me that up here. So the teacher believes, so this is my claim, that they spend 35 minutes on homework. She randomly asks some students how much they spend on homework. Hold on, let's go back here. The teacher believes the average number of minutes a student spends on homework every night is greater than. So greater than is going to be my alternative. Remember, my null is always equal. So my alternative here is that it's greater than 35 minutes. And I have a sample of 10 students, and I have a significance level of 10%. All right, so I'm going to get in here to my conditions. So first thing here is random, and it tells me that I have an SRS. She randomly selects 10 students, so that's good. All right, now I'm going to go to independence. And when I have independence, I have a sample size of 10, and that's less than 10% of all her students. All right, and now I'm going to check my normal condition, and my normal condition here is what I'm looking for. I don't have a proportion, so I know that 10 is less than 30, so I have to check the graph. So at this point, I'm going to haul out my calculator, and I'm going to go ahead and put all this data in my 1vars because I'm going to need it anyway. So I go into stat, edit, I'm going to list my numbers here. So let me clear this out. All right, so there's my 10 data points. And so now I'm going to go into stat plot. My stat plot's on. It's a histogram. I'm going to go ahead and graph it. Oh, my window's all messed up. So let me go here. Hold on, it's still cooking. Zoom, 9. All right, so here's my histogram. So if I look at my histogram right now, it looks very much skewed. All right, so if I look at my actual values here, I see that my value here, I go from 28 to 36. So what I'm going to do, this starts at 28 and this goes to 36 and it goes on. I am going to redo this with a different scale. So if I go into my window, I'm going to start, if I look up here, my low is 28. So I'm just going to start at 27 and I'm going to go to 70 and I'm going to make my scale 10. All right, and you see I'm just completely making this up right now, and I'm going to regraph it, and that looks a lot better, right? I have something that looks like this. Now, this is going to be a number, and this is going to be time. Don't forget you have to label it, if you even have to label it. This tells me this is going to be 4, and it goes from 27 to 37. This is going to be 3. And it's 37 to 47, 57, 67. And so that is what my histogram looks like. Now, I could go in and I can do a different scale again, but this looks pretty good. So what I'm going to say here is no visible outliers and no significant skew. And again, because I have my labels on here with my scale, it makes it easier to see what I've done since I've changed this up. And you should just see just by changing it by one number how much this changes your histogram. All right, so let me go into my calc. And what I have here is I know I'm running a test. So I have to ask myself, what kind of test am I running? I know it's a test because I go back to the significance level. Nowhere up here does it give me the standard deviation. So I don't know the standard deviation. So that means I have to run a 1 sample t-test. I have to calculate the tail, for means. So this is what I'm running. So first thing I'm going to do is I'm going to calculate my t-value. So my t-star value, which is x minus mu over my sample standard deviation, which is s over n. Now, I didn't write these values down, but I have all of my data that's in there, so I'm going to go in here and just run a 1-var stats, and now I can pull everything that I need right from this. So I know that my x bar is 42. I know that my claim is 35, so minus 35. My standard deviation is S, so that's 11.5, and my number of data points is 10. So when I plug this into my calculator, this gives me a t-star value of 1.924. All right, so what does this look like? So this is what this looks like. So I have this value here that's right here at 1.924, and what I'm testing is greater than. So this is the data that I want. I want this part of my tail. So if I want this part of my tail, I'm going to go in here to stat, and I'm going to run it. I'm going to do a distribution now, and I'm going to go down here to TCDF because I've already got my distribution, so I want to know what's in my tail. My lower bound is 1.924, my upper bound is 999, my infinity, and then my degrees of freedom. Now, I didn't list degrees of freedom anywhere, so I'm going to go ahead and do this right here so that they know that I know what this is. So it's n minus 1, which is 10 minus 1, which is 9. So my degrees of freedom are going to be 9. All right, make sure you've got that somewhere on there. All right, so what this does is it tells me that my p-value is 0.043. All right, so now here's my communicate. My communicate section is going to be, because our p-value is less than 0.10, and I'm just going to put this right here, 0.043 is less than 0.10, and remember this is my significance level. We reject the null. All right, we have convincing evidence now this is where my context comes in, that the number of hours a student spends on homework is greater than 35 minutes. All right, so same type of justification that we had when we did proportions. All right, so type 1, type 2 error. So again, this is not any different either. So what we have is we have our null, our hold on, let me write this down. I can't do two things. So here's my decision, and here's my truth. And so what we did, if I just write this down, so this was 1, this was power, and then this was a type 2 error. So here are all of my errors. So it says, describe type 1 and type 2 error in the context of the problem above. So this is my type 1 error. So type 1 error, I have rejected the null, right? So I favored the alternative hypothesis, so I rejected the null incorrectly. So in context, what does that mean? That means the average number of minutes a student spends on homework is greater than 35 minutes when it isn't. All right, and then my type 2 error, that's this one down here. My type 2 error is we failed to reject the null incorrectly. And what does that look like? We don't have evidence the number of minutes is greater than 35 when it really is. Okay, so if we think about this, so this was my type 2 error. What we have up here is that we rejected the null hypothesis. So we have an H sub A. So we rejected the null hypothesis, and if we would have had an error in this, it says to describe both, so we did. We would have had a type 1 error. We rejected the null incorrectly. So the average number of minutes a student spends on homework is greater than 35 minutes when it isn't. All right, that's it.